4,000 miles below our feet right now, the Earth is operating as a massive, continuously running thermal engine. Look at this cross-section of the planet. The glowing core and mantle hold so much thermal energy that extracting just 0.1% of it could supply all human energy needs for 2 million years. Yet, despite sitting directly on top of an inexhaustible reactor, geothermal power currently makes up barely 0.34% of the global electricity supply. This technical map highlights why. The red and orange zones show where tectonic activity brings crustal heat close to shallow groundwater. This creates rare geographic pockets, like Iceland, where we can easily tap into it. Right now, our access to this clean energy isn't determined by our engineering capabilities. It is dictated entirely by random tectonic geography. If a city isn't sitting on top of one of those rare volcanic hotspots, the only alternative is to dig straight down.
Quick interruption. If you're enjoying the video, subscribing really helps the channel grow, so I can make more content like this. It's completely free, and you can always change your mind later.
The further down you travel into the crust, the hotter it gets. This is the geothermal gradient, where temperatures rise roughly 25 to 30 degrees Celsius for every kilometer descended. This graph tracks the cost of traditional mechanical drilling against depth. Notice how the line stays relatively flat at first, but once it passes 5 kilometers, the cost spikes exponentially. Deep underground, the conditions become violently hostile to machinery. High heat damages the equipment, and dense granite wears down mechanical drill bits, snapping steel and forcing crews to waste millions of dollars halting operations to haul broken tools back to the surface. We are blocked from the planet's largest energy reserve by the simple physical limits of grinding steel against hot rock. In 1970, the Soviet Union tried to test the absolute limits of mechanical drilling. They created the Kola super deep borehole, which ended beneath this rusted, bolted-down metal cap at 12.2 kilometers. It took 2 decades of relentless grinding to reach that depth. By the time they stopped, the extreme heat had warped their steel pipes and melted their diagnostic instruments. To make next-generation geothermal energy viable globally, engineers calculate we need to push well past the Kola record and reach depths of up to 20 kilometers. This phase diagram illustrates what happens to water at those extreme depths. When temperatures surpass 374 degrees Celsius under crushing pressure, water transitions into supercritical steam, a highly energy-dense hybrid state that is neither a pure liquid nor a normal gas. Supercritical steam can yield up to 10 times more electricity than a standard geothermal well. But because reaching it physically destroys traditional drill bits, extracting it requires a complete departure from mechanical digging. This vacuum chamber is part of a gyrotron. It is a highly specialized piece of technology originally developed to heat plasma inside nuclear fusion reactors. Researchers use gyrotrons to fire millimeter wave beams down a waveguide, vaporizing basement rock past 1,500 degrees without contact. Compressed argon clears the vaporized rock crag upwards, while residual heat melts the borehole walls into a sealed, hardened glass lining. By replacing drill bits with directed energy, deep drilling becomes a controlled interaction between electromagnetic radiation and matter. If directed energy can bore 20 kilometers through solid granite, a power plant can be built almost anywhere on Earth, completely untethering energy wealth from geography. Currently, thousands of massive coal and natural gas plants make up the backbone of the global grid, carrying an enormous carbon footprint and requiring massive supply chains to feed them. Instead of tearing them down, gyrotrons can bore deep geothermal wells directly beneath existing fossil fuel plants. The supercritical steam piped up is the exact same temperature as steam created by burning coal. It feeds straight into the existing turbines to generate electricity. We can strip the carbon emissions out of dirty infrastructure by swapping the fuel source, while keeping the physical power plants and transmission lines completely intact. Moving this from a laboratory to a 20-kilometer deep well involves extreme, unsolved engineering hurdles. The delicate waveguides and magnets required to direct the beam must somehow survive intense underground pressures and temperatures exceeding 500 degrees. But solving those problems won't require starting from scratch. The deep drilling expertise, capital, and global workforce of the oil and gas industry can be seamlessly redirected toward this exact challenge. Humanity's most abundant power source isn't waiting to be invented. It has been safely humming beneath our feet since the formation of the planet. Securing this multi-million-year resource for human civilization now relies entirely on our ability to master the most hostile, high-pressure environment ever explored.